We're going to take a look at action potentials in this video. Action potentials are large, rapid changes in the membrane potential produced by depolarization. And they occur when graded potentials reach threshold at the axon hillock and open up the voltage-gated sodium and voltage-gated potassium channels. And action potentials are very different than graded potentials because they don't decrease in size. So they're very good for long distance communication, and they will travel down the axon to the axon terminal. Action potentials involve voltage-gated sodium channels and voltage-gated potassium channels. So make sure you remember that. That's really important. And voltage-gated sodium and voltage-gated potassium channels, remember, are found at the axon hillock and all the way down the axon. So they're going to open when the inside of the cell becomes depolarized or more positive and it reaches threshold. Remember that magic number of minus 55 millivolts. There are 3 phases to the action potentials, so make sure that you know these. There's the depolarization, repolarization, and after hyperpolarization phases. So here's what an action potential looks like. If we start at the resting membrane potential of minus 70 millivolts, how we get up to threshold where the action potential actually starts is through these graded potentials. And remember, the graded potentials are generated by ligand-gated ion channels that are in the dendrites and the soma of the neuron. And so if we reach threshold at the axon hillock, that'll open up the voltage-gated sodium and potassium channels, and that will start the action potential at threshold. And so we'll start with this depolarization phase first. So we'll become more positive. And then at the top here, we'll start the repolarization phase. And then once we reach threshold again, in the purple, this last phase is the after hyperpolarization phase, and then we go back to the resting membrane potential, and then the action potential is over. We're going to draw out what happens in an action potential. So we'll start down here at the resting membrane potential of minus 70 millivolts. And if we take a look at our voltage-gated sodium and voltage-gated potassium channels, the voltage-gated sodium channel has 2 gates on it. The gate on the top is closed. It's called the activation gate. And the gate on the bottom is open, and that's called the inactivation gate. So because the gate on the top is closed, sodium can't move in through the voltage-gated sodium channels. So nothing is going on at the resting membrane potential with that voltage-gated sodium channel. And then the voltage-gated potassium channel is much simpler. There's just 1 gate on it, and it is closed at the resting membrane potential, so potassium cannot move out through the voltage-gated potassium channel, so nothing's happening there. And remember the location of the voltage-gated sodium and potassium channels. They're going to start at the axon hillock. I've got a picture up here on the top right, and they go all the way down the axon. And how we get from the minus 70 millivolts up to threshold, where we're actually going to be starting our action potential, this part right here, this is due to graded potentials. And remember, those are going to be created by these ligand-gated ion channels. And those are located in the neuron dendrite and somas. So if we have this presynaptic neuron release neurotransmitter here, and we open our gate, and maybe this ligand-gated ion channel is specific for sodium ions, and we let sodium ions in, and we would have to have some other ligand-gated sodium ion channels also opening, or maybe this one will be firing rapidly in a row to reach threshold. But if we get enough sodium ions coming in, if we get a big enough graded potential, we can reach threshold at the axon hillock here, and that will start to open up our voltage-gated ion channels. And that will start the depolarization phase of the action potential. So the action potential actually does not start until you reach threshold at minus 55 millivolts. So we've got graded potentials going from minus 70 to minus 55 millivolts. And what happens at minus 55 millivolts at threshold is that both the voltage-gated sodium and voltage-gated potassium channels will both be triggered to open, but the voltage-gated sodium channel is going to be opening and closing much quicker than the voltage-gated potassium channel. So our voltage-gated sodium channel, the activation gate on the top is going to flip open. And remember that sodium always wants to go into the cell. So sodium is going to rush in, and if you have sodium coming into your neuron, that's going to make it more positive. So if we have our axon hillock over here, we've got our sodium coming in, you can see that's going to depolarize the inside of that neuron there. And our voltage-gated potassium channel is slow to open, so it has not opened yet. So it's stayed closed right now during the depolarization phase. And as sodium comes in and depolarizes the neuron, that's going to trigger the opening of more voltage-gated sodium channels, and that means more sodium will come in, and that'll depolarize the cell more, and then that'll trigger more voltage-gated sodium channels to open, and then we depolarize more, and so you can see that we get positive feedback going on. So the depolarization phase of the action potential is actually an example of positive feedback, because we're getting further and further away from the normal, okay? And then what happens at the top here of the action potential is that our voltage-gated sodium channel is going to close. So this inactivation gate on the bottom will close. And that's going to stop sodium from coming into the cell. So that'll stop the further depolarization. And then what's going to happen is that the voltage-gated potassium channel gate is finally going to open. And remember that potassium always goes out of the cell. And so if you have potassium going out, and then our voltage-gated sodium channel is still closed here. And so if you have potassium leaving the cell with its positive charges leaving, that's going to make the cell more negative inside, and so that's going to cause this repolarization phase. Okay, so this repolarization phase will go all the way until we reach the resting membrane potential down here at minus 70 millivolts. And this is a form of negative feedback. So So the repolarization phase of the action potential is a form of negative feedback because we're acting to return things back to the normal range to the resting membrane potential. Okay, and then our third phase of the action potential is this after hyperpolarization phase. So what happens here is that our voltage-gated potassium channels are going to be slow to close. So they actually don't close until the bottom here. So potassium is still leaving the cell past the resting membrane potential, and so the positive charges keep leaving, and so you get hyperpolarization. So you're going to get even more negative than the minus 70 millivolts. And then your voltage-gated sodium channel is actually going to reset here. So we're going to reset the gates to the original form of what they were. Okay, and then once the voltage-gated potassium channels finally close at the bottom here, we stop going any more negative than we already are. And then to get back up to the resting membrane potential, how we get back up there is through the sodium-potassium pump. So the sodium-potassium pump is going to put the sodium and the potassium back where they should be. Okay, so it's going to pump the sodium back out of the cell and pump the potassium back into the cell where it should be. Okay, and return the concentration gradients to where they originally were. And then that will be the end of our action potential once we return back to the minus 70 millivolts, our resting membrane potential. Okay, so I would definitely be able to draw out this picture. I won't make you draw it out on the exam, but if you can draw this out and explain what's going on in each of the three phases of the action potential, and be able to explain like what's going on like with the voltage gated sodium channel, and make sure you know like what's going on, you know, is the inactivation gate open or is it closed, and what's going on with the activation gate, what's going on with the voltage gated potassium channel, and know which phase has positive feedback, which one has negative feedback. Where are these voltage-gated channels located? Okay, they're in the axon hillock and all the way down the axon. How did we get from minus 70 millivolts up to threshold to even start the action potential? Those are from those graded potentials. Remember, the graded potentials are generated by those ligand-gated channels located in the dendrites and the soma of the neuron. Okay, and then how do we get from the after hyperpolarization back up to the resting membrane potential? Well, that was the sodium-potassium pump. Okay, so if you can draw this out and explain what's going on in all of these phases, you could answer any question I ask on the action potential on the exam. Okay, and then I just have everything written out here that we just went over. And then these are just some pictures from your book. And then again, just some more pictures of what we've been talking about. And then just more pictures from your book, just showing you the voltage-gated sodium channel with the two gates, the inactivation gate on the bottom and then the activation gate on the top. And make sure you know which gates are open and closed during the different phases of the action potential. And then this is just a nice comparison of the voltage-gated sodium channel on the left with the two gates. And then here's the voltage-gated potassium channel with just the one gate. And then the three phases of the action potential here so you can see which gates are open and closed there. Okay, and then just to answer some questions. So at the resting membrane potential, both the voltage-gated sodium and potassium channels are closed. No sodium or potassium are moving right now. And then during the depolarization phase of the action potential, we get the voltage-gated sodium channels that are open. So that means that sodium is going to move into the cell. And you get this positive feedback loop going on. And as you get sodium coming in, that'll have trigger more opening of more voltage-gated sodium channels. More sodium comes in, becomes more depolarized. More voltage-gated sodium channels open, more sodium comes in, more depolarized, so you get this positive feedback loop going on. Okay, and then at the top of the depolarization phase, you get the inactivation gate on the voltage-gated sodium channels that closes. And so sodium stops moving into the cell. So that'll stop the depolarization phase. And then the voltage-gated potassium channel is going to open. And so potassium, remember, moves out of the neuron. And as potassium leaves with its positive charge, that's going to cause the repolarization phase. And that creates negative feedback. And we return back towards the resting membrane potential. And the voltage-gated sodium channels will reset right near the resting membrane potential, and then we'll be ready to have another action potential again. And then the after hyperpolarization phase, those voltage-gated potassium channels are slow to close, so potassium keeps moving out. And the membrane potential is going to hyperpolarize. But then it finally, the voltage-gated potassium channels then finally close at the bottom of that, at the bottom of that after hyperpolarization phase. And then how we return to the resting membrane potential is through the sodium-potassium pumps. So they're going to put the sodium and the potassium back where they belong. Okay, and this is just a nice table from the book that goes through the phases of the action potential and then just talks about the voltage-gated sodium and potassium channels and talks about which ones are open and closed, and is potassium or sodium flowing in or out or not moving, what's going on. So this will be also be a good table to take a look at.